Welcome to the deep dive. Ready to explore some quantum mechanics?
Always.
Today we're diving deep into quantum applications, especially how they're shaping the future of computing and simulations.
Sounds fascinating. Where are we starting?
We'll be taking cues from an essay called Quantenanwendungen Simulationen für die Zukunft.
Yes. Quantum Applications. Simulations for the Future by Jörg O. Schneepatt.
Exactly. He does a fantastic job of simplifying some pretty complex ideas.
I agree. Schneepatt's insights into quantum technologies and their potential are remarkable.
It's mind-blowing to realize that quantum mechanics, something that governs the universe at such a tiny scale, already impacts our daily lives in big ways.
Absolutely.
Yeah.
Lasers, semiconductors, MRI machines.
Exactly. It's all thanks to quantum mechanics. And now we're stepping into an era where these technologies are set to revolutionize everything.
From computing and material science to medicine, the possibilities seem endless. Schneepatt even suggests.
Hold on. Before we get ahead of ourselves, let's make sure everyone's on the same page. Some key principles of quantum mechanics underpin these advancements.
Good point. Things like superposition, entanglement, the uncertainty principle. Schneepatt refers to them as the building blocks of a new technological revolution.
Let's unpack those a bit. What is superposition in simple terms?
Imagine a quantum system, like an atom, being able to exist in multiple states at the same time until we measure it.
It's like Schrödinger's cat, right? Both dead and alive until we peek inside the box.
Precisely. A mind-bending concept that challenges our classical understanding of the world. But in the quantum realm, things can be in multiple states at once. And that's what gives quantum computers their power.
Okay, so that's superposition. What about entanglement? Einstein called it spooky action at a distance, right?
He did. Imagine two particles linked in such a way that their fates are intertwined, even if they're miles apart.
Like two coins flipped simultaneously, always landing on the same side no matter how far apart they are.
Exactly. It's like they're communicating instantaneously, which, according to Einstein's theory of relativity, shouldn't even be possible.
Right. But experiments have repeatedly confirmed that entanglement is a real phenomenon, a key player in quantum computing and communication.
Schneepatt even suggests that harnessing entanglement could lead to ultra-secure communication networks, completely immune to eavesdropping.
Now that's what I call a game changer. Okay, one more principle to clarify. The uncertainty principle.
This one, formulated by Werner Heisenberg, states that there's a fundamental limit to how precisely we can know certain pairs of properties of a particle.
Like the more precisely we know a particle's position, the less we can know about its momentum.
Precisely. It's not about our measurement tools being flawed. It's a fundamental law of nature.
So these seemingly bizarre quantum principles, which seem so counterintuitive to our everyday experiences, are not only real, but also the foundation for this whole new technological revolution.
And Schneepatt really drives that point home in his essay. He argues that these principles are the keys to unlocking a world of possibilities we once thought were pure science fiction.
Speaking of which, let's dive into one of those possibilities, quantum computers. What sets them apart from the classical computers we use every day?
The key difference lies in how they process information. Classical computers use bits, which can be either 0 or 1. Quantum computers use qubits, which can be in a superposition of both 0 and 1 at the same time.
Like our spinning coin analogy for superposition, right?
Exactly. A qubit can be both possibilities at once until we measure it. That's what gives quantum computers their edge, allowing them to explore many possibilities simultaneously and making them exponentially faster for certain calculations.
So what happens when you have multiple qubits working together?
That's where entanglement comes into play. Entangled qubits have their fates linked, allowing quantum computers to perform calculations that would take classical computers an impractical amount of time.
It's like a team of superpowered calculators, all working in sync.
A great analogy. And this ability to harness superposition and entanglement is what makes quantum computers so revolutionary.
Now, I understand there are different types of quantum computers being developed. Schneepatt touches upon this in his essay, mentioning superconducting qubits, trapped ions, and photonic qubits. Can you give us a brief overview of these approaches?
Sure. Superconducting qubits, the kind companies like IBM and Google are working on, are basically tiny circuits cooled to extremely low temperatures where they exhibit quantum properties.
They need to be kept in those massive refrigerators, right?
Yes. They're quite well developed, but susceptible to environmental noise. Then there are trapped ions, where individual atoms are trapped using electromagnetic fields and manipulated with lasers. Companies like IonQ are focusing on this.
Each with its own strengths and weaknesses. What about photonic qubits?
Those use particles of light, photons, to carry information. They're less noisy than superconducting qubits and have potential for long-distance communication, which is essential for a future quantum internet. But creating stable and controllable photonic qubits is still a big challenge.
It's amazing how researchers are pushing the boundaries with these different quantum technologies. Now, Schneeplatt argues that the true power of quantum computers lies not just in the hardware, but in the algorithms we develop for them. He specifically mentions Shor's algorithm and Grover's algorithm.
Absolutely. Shor's algorithm, for instance, can factor large numbers exponentially faster than any known classical algorithm. This has huge implications for cryptography, as many encryption methods rely on the difficulty of factoring large numbers.
So Shor's algorithm could potentially crack the codes that protect our online transactions.
It raises concerns about cybersecurity, yes, but it also pushes us to develop new quantum-resistant encryption methods. It's a constant back and forth, made even more complex with quantum mechanics in the mix.
Fascinating. What about Grover's algorithm? What makes it stand out?
Grover's algorithm offers a significant speedup for searching unsorted databases. Imagine looking for a specific grain of sand on a beach. Classically, you'd have to check every grain. Grover's algorithm lets you search much more efficiently, useful for tasks like database searches and optimization problems.
From cracking codes to finding needles in haystacks, these algorithms have the potential to change everything.
It's not about shortcuts. It's about understanding and using the laws of nature to our advantage. And this is where the work of researchers like Jorgo Schneeplatt is so vital.
His insights into quantum algorithms are paving the way for this groundbreaking technological revolution.
He makes a compelling case for investing in both hardware and software development to unlock the full potential of quantum technologies.
Absolutely. And on that note, we'll dive into another fascinating area, quantum simulations, after a short break.
Welcome back. Before the break, we were deep in the realm of quantum algorithms. Now, let's shift gears and talk about quantum simulations.
Ooh, quantum simulations. Sounds futuristic.
It does, but it's a very real and incredibly powerful application of quantum mechanics. We're talking about using quantum systems to simulate other quantum systems.
Okay, I'm following so far. But why is this such a big deal? Can't we just use classical computers for these simulations?
Good question. Classical computers are great for many things, but they struggle when it comes to simulating complex quantum systems. The computational resources needed just explode as the system gets bigger.
Like trying to fit a whale into a bathtub.
Exactly. Classical computers just can't handle the sheer complexity of quantum interactions. That's where quantum simulations come in. They use the same principles they're trying to study.
So instead of crunching numbers, they're speaking the language of the quantum world.
You got it. This approach allows us to study systems that are way too complex for even the most powerful classical computers. Think about simulating molecules, the interactions of electrons and materials, even processes inside stars.
Simulating stars. Seriously, what kind of practical applications are we talking about here?
The potential is enormous. In chemistry, for instance, quantum simulations could revolutionize catalyst design for cleaner energy, lead to new materials with tailor-made properties, even help create new drugs with fewer side effects.
It's like having a virtual lab where we can experiment with matter at the atomic level.
That's a great way to put it. Jorgo Schneeplatt, the author of the essay we're discussing, particularly highlights the potential for quantum simulations to transform materials science. Imagine designing materials with specific properties, like superconductivity at room temperature, or materials lighter than air but stronger than steel.
Now we're talking. Sounds like quantum simulations could unlock a whole new era of technological advancements. What specific simulations are researchers working on right now?
Well, one area where quantum simulations are already making waves is in the study of the hydrogen bond.
A hydrogen bond, isn't that pretty basic?
It seems simple, but it's crucial for tons of chemical and biological processes. Simulating it accurately on a classical computer is surprisingly difficult.
So it's everywhere, but hard to model.
Exactly. With quantum simulations, though, we're starting to uncover its secrets, getting insights into how it influences chemical reactions, protein folding, the properties of water.
Amazing how something seemingly basic can have such far-reaching effects. What other exciting simulations are on the horizon?
Another fascinating area is the simulation of complex magnetic systems. These are crucial for data storage, energy generation, even medical imaging. Understanding them better could lead to new types of magnets for more efficient motors, generators, even levitating trains.
Levitating trains, sign me up. But seriously, it's mind-blowing that we're just scratching the surface of what's possible with quantum simulations. What's holding us back from simulating, say, the entire universe?
Well, like any new technology, there are challenges. One of the biggest is the limited number of qubits in current quantum computers. To simulate truly complex systems, we'll need computers with thousands, maybe even millions, of stable, interconnected qubits.
So it's about both quantity and quality of qubits.
Exactly. And we also need to develop better, more sophisticated algorithms specifically designed for these simulations. This is where Schneepat sees a huge need for more research and investment.
Sounds like a long road ahead, but the payoff could be incredible. Schneepat argues that quantum simulations could revolutionize not just specific industries, but our entire approach to scientific discovery.
It's not just about faster calculations, it's about gaining deeper insights into the fundamental laws of nature.
Now, Schneepat doesn't just focus on the science. He also delves into the broader societal and economic implications of this quantum revolution.
Absolutely. He recognizes that the quantum revolution is not just technological, it's societal. And with any powerful new technology, we need to consider both the potential benefits and the risks.
So let's start with the good stuff. What are some of the potential benefits quantum technologies could bring to society?
Well, for starters, they could lead to personalized therapies and more effective drugs, help us find sustainable energy solutions, even enhance cybersecurity through quantum-resistant encryption methods.
A future filled with possibilities. But what about the potential downsides? What risks should we be aware of?
One concern is the potential impact on cybersecurity. As we discussed earlier, powerful enough quantum computers could crack the codes that protect our online data, putting sensitive information at risk.
So we need to develop and implement quantum-resistant encryption methods, like yesterday.
Exactly. Another concern is potential job displacement. As quantum computers become more capable, they could automate tasks currently done by humans, leading to job losses in certain sectors.
That's a valid point. But wouldn't these technologies also create new jobs and opportunities in emerging fields?
Absolutely. We'll need a workforce skilled in quantum computing, quantum engineering, quantum software development. Investing in education and training programs is crucial to prepare the current and future workforce for this quantum future.
It's about being proactive and adaptable, not getting caught off guard. Schneepat emphasizes that this quantum revolution will require us to rethink our approach to education, workforce development, and even our understanding of what it means to be human in a world increasingly shaped by these technologies.
He's right. We can't just blindly adopt new technologies without thinking about their impact on society. We need to have open and honest conversations about these issues and make informed decisions about how we want to shape this quantum future.
That's a great point. As these technologies keep evolving at such a rapid pace, how do we make sure they're used for good and that everyone benefits?
Schneepat argues that we need to establish ethical guidelines and regulatory frameworks for the development and use of quantum technologies. We need to address concerns about bias, discrimination, and the potential for malicious use.
It's a tall order, but an essential one. Schneepat's essay is a call to action, urging us to have these critical conversations and work together to create a quantum future that benefits all of humanity.
I couldn't agree more. We're at a crossroads, and the choices we make today will have a ripple effect on the quantum revolution and its impact on the world.
Speaking of the future, I'm curious to hear your take on what lies ahead for quantum technologies. What breakthroughs are on the horizon? What challenges still need to be tackled?
The future of quantum technology is incredibly exciting. We're on the cusp of a new era where quantum computers will become even more powerful, able to solve problems we can only dream of today. And as we explore this strange and beautiful quantum world, who knows what other mind-boggling applications we'll discover?
It feels like we're explorers setting foot on a vast, uncharted continent, just beginning to grasp its potential. Welcome back to the Deep Dive. We've covered a lot of ground exploring the fascinating world of quantum mechanics and its mind-boggling applications. As we wrap up our deep dive into Jorgo Schneepat's essay, Quantenanwendungen, Simulation für die Zukunft, what stands out to you as the most crucial takeaway?
For me, Schneepat's most powerful message is a call to action. He urges us to recognize the immense potential of quantum technologies while also being mindful of their ethical and societal implications.
Right, acknowledging that we're not just watching this technological revolution unfold, but actively shaping it.
Exactly. Schneepat also stresses the importance of collaboration. Scientists, engineers, policymakers, the public, we all need to work together to ensure these powerful technologies are developed and used responsibly.
breaking down silos and fostering open communication, as he suggests.
Absolutely. To effectively navigate the complex challenges and opportunities that come with quantum technologies, we need diverse perspectives. That means addressing concerns about cybersecurity, job displacement, and the potential for these technologies to worsen existing inequalities.
Making sure the benefits of the quantum revolution are shared by everyone, not just a select few.
Precisely. Schneppat's essay is a valuable roadmap for navigating this uncharted territory. He provides insights into the potential benefits and risks of quantum technologies while emphasizing ethical considerations and responsible development.
His work underscores the need for informed decision-making, public engagement, and a commitment to using these powerful advancements for the greater good.
It's not just about pushing the boundaries of what's scientifically possible. It's about shaping a future where quantum technologies are a force for good in the world.
Well said. As we conclude our deep dive into the quantum realm, I want to leave our listeners with a final thought, inspired by Schneppat's essay. As we venture deeper into this world, we're bound to encounter new mysteries, new challenges, and new ethical dilemmas. How do we, as individuals and as a society, prepare ourselves for the unknown? How do we cultivate the wisdom and foresight to navigate this uncharted territory responsibly?
That's a profound question. I believe the answer lies in fostering a culture of curiosity, critical thinking, and open-mindedness. We need to approach the unknown not with fear, but with a sense of wonder, a willingness to learn, and a readiness to adapt.
Recognizing that the quantum revolution isn't just a technological shift, it's a fundamental shift in our understanding of the universe and our place within it.
And as we grapple with these profound changes, it's crucial to remember that the future is not predetermined. We have the power to shape it. It's our responsibility to ensure that the quantum revolution leads to a brighter, more just, and more sustainable future for all.
Absolutely. Thank you for joining us on this incredible journey into the quantum realm. And to our listeners, we encourage you to continue exploring, questioning, and engaging with this transformative field. The quantum world is full of wonders, and who knows what groundbreaking discoveries await us. Until next time, keep those minds expanding and those questions flowing.